Good morning once again. In this problem, I would like to deal with simulating a pump. In fact, some of such problems you might have worked using Bernoulli's theorem. Most of those problems involving Bernoulli's theorem can also be simulated, and you should be in a position to solve such problems. For example, water at 60 degrees Fahrenheit is to be pumped from a reservoir, open reservoir, to the top of a mountain through a 6-inch steel pipe at a rate of 200 gallons per minute. The pipe is required to discharge water into the atmosphere at a level of 3000 feet above the level in the reservoir. So there is a height difference of about 3000 feet. The pipeline is 4500 feet long and contains 2 gate valves, 4 standard T's and 4 elbows. Suggest the rating of the pump required to meet the above purpose. So you should be in a position to solve this problem using Bernoulli's theorem and identify the necessary terms involved in the Bernoulli's theorem if you want to solve it analytically. Now let us try to simulate this problem. As you can see, again, we are going to make use of only one component in this simulation, which is water. So the property method that can be used for water or steam, it is better to select steam tables. So go to the next input screen, go to simulation environment. Now you have a pump which need to force water through this pipeline. So initially I am using a pump, and the difference between pipe and pipeline is if you have a single segment pipe with constant diameter and rise, which can also include fittings, you can use this model. Whereas if you want to go for pipeline, you can see here multiple segment pipeline. Segments may have different diameters. As far as this problem is concerned, we have a uniform diameter pipe, so we should be able to use a pipe model to represent this particular problem. So let us connect the input and output. Now you know already the details are given to you. The pipe has some fittings, and the water that is being pumped from a reservoir, the outlet is above 3000 feet, and the pipeline is having a length of about 4500. So essentially the pump, you need to calculate the rating of the pump, the capacity of the pump, the power required by the pump in order to force water across this pipeline, which is having a length of about 4500 feet and over a height of about 3000 feet. So whatever may be the pressure drop in this entire pipeline across the fittings, you should be able to increase the pressure of water by using this pump, so that water will be able to come out from the exit of this pipe at 3000 feet height. So let us go into the problem statement, definition of the problem. So water is available at 60 degrees Fahrenheit because it is an open atmosphere. The reservoir is open to atmosphere. You can think of using atmospheric pressure, that is the inlet. The flow rate is 200 gallons per minute. So let us specify this data. 60 degrees Fahrenheit. So let me change the unit system. So we have 60 degrees of temperature. Pressure is atmospheric pressure, maybe 1 bar or 1 atmosphere. And the flow rate is in terms of volumetric flow, 200 gallons per minute. So we have satisfied the definition of stream 1. Now we are required to look into the other input that may be required in order to complete the problem definition. So we are using a pump. So will we be able to identify the discharge pressure? To what extent pressure must be increased to overcome the pressure drop in the pipeline? See, without solving the model, we will not be able to know what is the actual pressure drop that is happening in the pipe. So let me assume some value. Let me convert this into again bars. Maybe some 10 bar or let us say 50 bar, for example. This is a wild guess, right? Next. Now the pipe length is 4,500 feet. So we are going to use pipe schedules. We are given that the material is carbon steel, schedule 120, and the nominal diameter is 6 inch. All this data is given in your problem statement. 6-inch steel, schedule 120, right? So now you can see the required input is complete. So you should be able to run the program. The moment you select the material of construction from the database, it has calculated or it has taken the roughness as some value. If you are happy with this value, you can go ahead. And if you have some experimental value for the given pipe, you can also replace this value with an appropriate roughness value. Okay. So let me run this simulation. Now, thermal option is required for single component model unless n phase is 1 is specified. We saw this problem earlier. So what is happening here? So just 1 second. I think we did not complete the details. Sorry. We did not specify the elevation. Pipe rise is 3,000 feet. This I missed earlier. And we can say flash options, and instead of vapor liquid, you say only liquid. Right? That takes care of that problem. Again, within the pipe, you want to talk about some fittings. Some fittings are given in the problem statement. 2 gate walls, 4 standard T's and 4 elbows. 2 gate walls, straight T's, maybe 4, and what is the other? 4 elbows. So you can add, if you have other things, you can also add. In fact, some more fittings are also available here. If there is an enlargement or contraction, that can also be considered. Right? We reset the simulation and run it again. Now you can see there is an error. Right? So pipeline integration failed at iteration 112. So current length is about 2,516 feet. By the time, what is happening to the pressure? The pressure is coming down to a very small value. That means the pressure drop in the pipe is more than the 50 bar that you are compressing using the pipe. So with this 50 bar increase in pressure from the inlet 1 bar, we were able to force flow only through a distance of about 2,500 feet, right? But the pipe length itself is 4,500. So whatever value that we have selected here is not able to force flow across the entire pipeline, right? So that means we need to increase the pressure to which this liquid must be compressed in order to handle this pressure drop so that flow will happen across the entire pipe and you should be in a position to deliver. Ideally, unless and otherwise the pressure coming out of this pipeline is slightly more than the atmospheric pressure, there may not be any flow happening. So it should be able to handle the entire pressure drop in the entire pipeline, and the exit pressure must be slightly above atmosphere. So again, we don't know what is this value. So let me consider something like 100 instead of 50. Okay, next. Now once again you can see if you are able to compress now previous, let me reinitialize. Do it in discharge pressure. So we were let us see the control panel. So we were able to come to the conclusion, and now let us see the pressure at the exit. Now you can see the units. Though you are increasing, what is the inlet pressure to the pipe? It is at 100 bar. but the exit pressure is about at 9.56 bar. That means roughly about 91 bar of pressure drop is happening within the pipe. That's why the previous assumption of 50 bar was not able to push water through the entire pipeline. Probably we don't have to compress it to 100 bar. We are having more pressure than the atmosphere. So you may be able to reduce it by about 8 or 9. You can do that. Now the issue here is not exactly that. You can look at the results of this pump. Now you can see what is the power required, network required by the pump. So you are required to at least, this is the capacity of the pump in order to force flow in the given problem. If you want, you can convert this. So this is a huge rating of the pump. Unless and otherwise you are able to use this much of rating for the pump, you will not be able to achieve the flow through this particular pipeline. And you can also similarly look at the results of this block. Now you can see the total pressure drop is, let me convert this into bar, about 90 bar. So the pump, the inlet is at 1 bar for the pump. Unless and otherwise it compresses to more than 90, we will not be able to achieve flow across the entire pipeline. So out of this 90 bar, 9.33, yes, if you try to put it. So the frictional pressure drop is quite small, whereas the elevational pressure drop is quite high in this problem because the elevation itself is about 3000 feet. So the head lost due to friction is only small compared to the head lost due to the elevation or the potential energy. So you can probably look at this. Now when you try to simulate the flow through a pipe, using a pump, there are two options for you. If you are giving the discharge pressure, it will try to calculate the power required in order to discharge water at this high pressure. Or if you try to specify the power of the pump, suppose if you say 10 HP, then it will calculate at what pressure it will be able to discharge. So either of these you should be able to use while simulating a particular pump. So probably other simulators, you may not be able to find out this data. In case if the pressure drop is more than the inlet pressure, you may be getting some kind of an error. But Aspen will clearly show you with the available pressure to what length you will be able to have the flow. And that will give you exactly some idea about the kind of pressure to which water must be compressed in order to deliver water at the exit ultimately. So I would like to stop this demonstration with this.